Good morning, everyone. Welcome back to the third and final day of ILLS6. If you can all take your seats, we will start with our first invited talk. The speaker will be introduced by Clara.
Good morning, everyone. So my name is Clara Marian. I'm a graduate exchange student here in the linguistics department. And as you probably know, there has been a change in the schedule due to Professor Haring's illness. But I am very happy to introduce our replacement instead. Dr. Chilin Shih was very kind to agree to speak on very short notice. So we're very grateful for that. Dr. Chilin Shih is a Helen Corley Petit Scholar and Associate Professor in Linguistics and East Asian Languages and Culture here at the University of Illinois. She got her PhD in Linguistics at the University of California in San Diego in 1986. And Dr. Shih works primarily with tone and prosody representation and modeling and how these can be applied within second language teaching. And she has also completed an articulatory-based prosody modeling platform called Soft Template Markup Language. I'm not sure whether we'll hear about that today or not. In this presentation, Dr. Shih will talk about measures of Chinese lexical tone difficulties and how second language item difficulty ratio can be explained by acoustic properties of tones, range of production variation, and confusability. So please help me in welcoming Dr. Shih.
Thank you for having me here. It is always a great pleasure to talk about this piece of work, which has been going on for many years. In this talk, I will be focusing on the measures of tone difficulties, but before I get into that area, I will be talking a lot of the background information, such as what kind of platform that this concept is applied to. So the research goal in this particular project is to develop an adaptive method for second language learning, in particular training. I will explain soon what adaptive training means. For the purpose of building an adaptive system, we need to automatically rank the difficulty level of speech sounds. And then we need to understand how second language learners acquire new tones categories and what might lead to their confusion. And we like to go into acoustic analysis to explain this. So first of all, what I'm talking about is primarily for English learner learning Chinese lexical tones. Here are the meaning differentiating lexical tones of Mandarin. Ma means mother, ma means hemp, ma means horse, ma means scold. So therefore, mama mama is mother scold the horse, and mama mama is the horse scold mother. That's just to prove to you that lexical is very important to learn. So what is it required for second language learner to acquire tones? Tone learning is one very unique aspect of second language learning in the sense that second language literature or theory rests on how a learner uses their L1 category to transfer successfully or not successfully into second language, that is L2 learning. But tone learning, we actually have reasons to believe that you need to build brand new categories. That is how an adult learner builds a new categories as opposed to a child building a new category. Why is that? Maybe in the next slides. Why is that? It's because English speakers, when processing long-term prosodies like question intonations or statement intonation, this information is appreciated by the right hemisphere. But lexical tone, being a phonemic contrast in Chinese, that is appreciated by the left hemisphere. So you actually have to build or shift the preferences in the right and left sides of the brain. In that sense, building new lexical tone category is a brand new task. In addition to that, what learner has to do is to learn F0 cues, not which for lexical tones, such doesn't matter to have different height, slope, shape, duration, intensity, creakiness, or the interactions of all of them. For lexical tones in Mandarin, it is a property on the syllable. Therefore, F0 chunking from a sentence level prosody to a syllable size, fast movement is another task that needs to be learned. There is also necessity for learning the association between tone and morpheme and word, but in this study, I completely bypassed the problem by only asking people to identify the tones in monosyllable tones. Okay. Our belief or our method of training is to give speakers highly variable speech sounds rather than the standard typical classroom renditions of ma, 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 carefully rendered. We believe that a speaker, a learner, has to go out into the society or the streets and encountering all different sorts of tone renditions like ma and ma, and soft and loud, high and low. And it's better for them to be exposed to this kind of stimuli to learn. So we plan in a very early stage to bombard the learners with the very stimuli, including exaggerated and reduced. And we also know that by giving early learners very confusable stimuli do not help them. Therefore, we use adaptive training system to present the stimuli in sequence of difficulty level. So this is why you know that I care very much about ranking the difficulty level of the tone stimuli. Okay, so how do we obtain highly variable speech? There are many ways of doing it, but then we chose, for experimental purposes, we chose one particular method that we use a physical distance between listener and talker. This is called the talker-listener distance to control the variation of the speech. So the idea is that if people are talking to people who are standing far away, then your voice will be louder, your pitch will be raised, and that of course would change the shape and the representation of the tone a lot. And if people are very, very close to me, like I'm talking to this microphone, then the voice maybe, you see that my voice is immediately dropped because I'm just talking to something that is very close, as opposed to if I'm talking to people standing by the table, then my voice is raised. So people respond naturally to listener-talker distance, and we're manipulating this particular aspect to get highly varied tone stimuli. We do not include other things, such as deliberately asking people to talk softer, louder, or longer, shorter, slower, faster. Those aspects we'll hope that will come out naturally from one single control of the experiment. So we have 11 distance defined between talker and distance. The microphone, the recording setting never changed during the entire recording process, but we put a person at different marker on the floor and asking the speakers to talk to the person standing there, and the person who was standing there was only smiling and encouraging the speakers to talk to them and making eye contact without saying anything. Okay, so so that was the stimuli, and then how does it fit into adaptive testing and training? So adaptive testing naturally was a computer-based concept, but it actually exists way before the development of computer. You know about the intelligence test, IQ test. So when Alfred Binet developed the IQ test, he actually have human-based or assistant-based adaptive testing, in a sense that he has stack of IQ-related questions sorted by different bins of difficulties. And then when the people come in, they will actually ask them questions and see where roughly they stay. And the system is very trained with the nature of the questions and the type of the question. So they will actually go to different piles. Depending on people's answer. So that was a humanized computer system. What is the advantage of the adaptive testing? And I always use the concept for training as well. If you use a fixed item test, then if your testers have very, very diverse background, then some people has to do some questions that are way beyond their capability and they get very frustrated. And some people will be doing some questions that are way easy for them and they're bored. So adaptive testing allows you to identify or specify a tester's level with a relatively fast speed without using irrelevant topic. This concept, again, implies that you know if people know about more difficult areas, then you assume that they know the easy ones. So for second language acquisition, we think that this will be an effective way of doing testing as well as training. And so we need a paradigm to present the right level of the exaggerated or reduced sound stimuli to the learners. So that's the goal. So the objective for adaptive testing is to find out the test level speedily and accurately. Adaptive training is to train students to acquire a skill in the most efficient way. These two problems will be infinitely hard and difficult if we say we want to find out the most speedy and accurate way of identifying a tester's level, and we want to find the most efficient way of teaching. And what I'm presenting is an approximation. I know that I haven't got there. And this is the graphic representations of what an adaptive testing system look like. So if I have items that are the little dots lining up from easy to difficult, then I want to find the fastest way as the tester come in to identify this is where the tester belongs or this is where the testers belong, and then I want to use the fastest method to report an accurate score. For training, what you want to do is to take a learner who by definition starting from nothing but go from the easiest stimuli all the way to the most difficult way, stimuli in the fastest possible way. So the components of an adaptive system include item banks, so that's our tone stimuli, an algorithm for when to start and when you're going to present the next stimuli, and selecting the next item to present to the learner or tester, scoring, if that is multiple choice question, that's actually easy, and you need to decide when to terminate. So this is hard to decide, therefore we just terminate it when the time is up, like 20 minutes, that's today's training. We also need a software for data presentation and collection. The advantage for training is that we can present graded material, and that is the concept of scaffolding. We are presenting easy material fast, but we do not dwell on it, so if the learner has learned it, we quickly move out to the next stage. It functions as a personalized tutor who knows all of the materials that is involved. So for testing, it shortens the testing time in the sense that you don't use the irrelevant test items. And then you can reduce the frustration for multi-level tester, as we said earlier. Okay, so now let's go on to the particular problem we're facing with training learners with Mandarin tones. Our data bank includes monosyllable tones, and then we have a problem identifying the difficulty level of those items, because native speakers, like teachers, have no clue. If the teachers know something very well, the teacher has no clue what the students are facing. And the native speakers have categorical perception, or at least some level of categorical perceptions. If I present any tone stimuli to the native speaker, they will say, this is tone 1, tone 2, tone 3, and tone 4, very quickly. And I say, which one is more difficult? I say, they're all easy. Our data bank was ranked and filtered by native speakers, and they are identified 100% correctly. And then native speaker has no clue which item is more difficult for the students. So it has to be the students who take the task to tell us which item is difficult and which item is hard. But before I implement the system, how do I get that score? So in the very beginning, we bootstrap the system by using the distance. And then the later level, we swap in the student's identifications rate of the tones to replace the difficulty levels. This is one thing. The other thing is these are the difficulty level of speech sound, which is very different from the traditional ranking of the difficult level that's based on, say, curriculum levels as well as text. Curriculum level is like addition and subtraction is easier than division and multiplication. And then they are all easier than algebra, and they're all easier than calculus. So that's easy. If you have some items in different first grader and 16th graders, then you, at K16, I mean college students, then the items is ranked by when you learn them. And for text, we also have some guides, such as longer words are harder than shorter words. Longer texts are harder than shorter texts. But how do you rank sound files that are of identical length that are monosyllables? So we have to use acoustics. So I have already talked about this. Let's skip over. Just briefly introduce to you what are in the data bank. They are monosyllable Chinese tones, 15 syllables chosen to cover diverse syllable structure. We have the syllables occurs with all 4 tones, so there are minimum sets. There are 3 speakers, 11 distance, 4 repetitions, about 8,000 speech files to train speakers to learn 4 tones. 2 native speakers identify the tones, and then any mistake, even if that's typing mistake, would disqualify the tones. Because we have many, so we can't afford to do that. We ended up with about 7,700 tones for the training in the data bank. So we present the tone and syllable one at a time for tone identification. A student entered the program at the midpoint, like level 6. That is, the recording distance in the middle. So we will see we have a chance of this for the students to move forward and move backwards. And then if they have to correctly identify 12 stimuli in a row to advance to a higher level. So this is to guarantee that there's no guessing. They don't succeed by chance. But then if they make 2 consecutive errors, we drop them to a lower level. That is, again, leaning toward heavy penalty for making mistake, and it's harder to get reward. Again, we don't want students to graduate by chance. That is why we implement it that way. But if they graduated, if they answered the 12 items in a row in the most difficult levels. And then if they graduated from the system, they don't have to come back. That means they take the rest of the training time for fun, having a cup of tea and coffee. Okay, so we also have some testing on the adaptive system. We had an experiment testing four different way of training. For example, the red team is a control group that has no training for tone. The green team was trained on less varied input, simulating the classroom teaching situation. The blue team is trained on the varied input, like all stimuli was used, but without using an adaptive system, competing with the orange team, the UIUC color for the adaptive team. And then here are the results. Okay, so here is the training schedule. They do the pre-test with 144 items. They go through 5 days of training. For each day, they have 144 items from the respected pool of data. And then the red team was doing lexical, like English translations of the lexical. There's no tone, and no sound files in their control. And then after 5 days of training, they come back for the post-test, and the participants conveniently come from 4 sections of the Chinese class, and then they are randomly distributed into semi-randomly distributed, because we want the same number of people in different teams. So they are distributed into the 4 teams, and there are 40 people complete the training. And the result is, the only significant result is that the orange team, the adaptive system, are significantly better than the control. The others are better than the control, but it's not significant. The result is not significant. And here is the the histograms of the training results. If the red team, the control, has almost normal distribution centered on 0, this is like how much they improve, how much the post-test improve from the pre-test. If they are 0, that means there's no improvement, which is good because it's the control. The interesting thing is the green team, everybody improved. Those are the ones that are using less varied classroom-like training material. This is the adaptive training, but this is the material we're using highly variable material in the blue team. That means 2 people were actually confused by the material and regress from the pretest. So if you look at this picture, the green team, most people improve, but they improve very, very little. In the adaptive, if you train people with varied test, some people can improve a lot. And in the green seems to be the red folding into the positive. And then the orange, the adaptive team, seems to be the very stimuli folding into the positive. That is, you take the negative, that's it, they take away the disadvantage and make it into an advantage. Nobody regress in this 2 training condition. But it's some people improve, some people didn't improve. Some people were actually hurt in this 2 condition. That is the control, that is the expected situation. But what we really want, what really shows is that people are helped a lot by varied, highly variable stimuli in training, but it helped them a lot if you present the stimuli in order. I mean, that's a concept of scaffolding. If you just throw different stimuli at random to them, some people really got confused. So that's the idea. That's the basic story. Okay, so we have talked about that. We also measure the effect size. The effect size is how many standard deviation do you improve from the pre-test to the post-test. So the orange team has more than 1 standard deviation of improvement. That is quite considerable. Okay, so all of those are preambles for the next part, the acoustic analysis and error analysis of the tone files. So for that, we are using analysis typically used in testing, the testing literature. So what are item analysis? In the basic idea is that you analyze each item in your test bank. You want to see, so the basic idea is that if an item is difficult, then you expect the good students to get it right and the bad students to get it wrong. If the picture is reversed, you have an item and the good and bad is just your total score. Like if you get 100 from the, you get 100% in the test, you are a good student. If you get 0% on the test, you're a bad student. So if you get 10% and you got the most difficult question right, then in the testing literature, they say there's something wrong with our test items. So we should eliminate that test items. But we have already ranked our acoustic stimuli by native speakers. We know that native speaker got all of them right. So we say if the acoustic property confuse the students, so the students who are less familiar with the tone stimuli got it right, but the students who are more familiar with the stimuli that got it wrong, we are actually very interested in the stimuli to see what kind of acoustic property leads to that result. So based on that idea, I do not discard any of the items after native speaker has filtered them. Okay, so we measure item difficulty. So item analysis measure item difficulty by the percentage of students who answer an item correctly. Item discrimination is the ability of a test item to differentiate student level. So item discrimination means how good, how different are the good students and the bad students answer this question. You want to see a big difference. And then because we only have acoustic property behind the monosyllable tones, what we want to do is to tie in the acoustic property with the item discrimination and item difficulty. Okay, so first of all, just to give you a broad sense of whether the distance in identifying item difficulty level. It turns out that these are the students' percentage error, like 25% errors, 24% errors based on the distance of the recording. So distance 11 is actually better. Originally, we think exaggerated stimuli will make things easy. So in that sense, we should see the curve coming down like this. Right now, what we found is that level 4 or 5 are the easiest stimuli, meaning the students are actually most comfortable with this distance of speaking, that is about 8 feet. That's basically the classroom distance. That is what our tests are coming predisposed, because that is what their teacher, their TA, used that kind of level to talk to them. And then they actually improve when the stimuli were exaggerated. They actually degrade as the stimuli were exaggerated. So now we understand that the exaggerated stimuli were actually distorted from the standard tone shape that they were exposed to in the classroom. And then the soft, the close distance, very, very hard for them because they're highly reduced, and they're actually the most difficult items for them. So this shows the item difficulty level based on distance. And then here is the plot that gives you the individual stimuli presented in heat scale. So the tone that are produced at distance 11 was plotted in yellow, and distance 1 was plotted in red. This is closer, this is further away. So you can see that a yellow float on top of red for the speakers in at least high level tone and falling tone. In the tones with concave shape is harder. The high part of the curve is higher, but the low part of the curve is not necessarily higher. So that is the individual differences on recording distance. Another speaker, same pattern. Another speaker, we have 3 speakers, similar patterns again. Slight difference. You can see that this is particularly clear that it's stratified, reflecting the recording distance. Okay, so here's the tone confusion matrix in the raw score. Notice native speaker are 100% correct. So native speakers, all tones are falling in the diagonal. That is, tone 1 is recognized as tone 1, tone 2 recognized as tone 2, tone 3 recognized tone 3, tone 4 recognized as tone 4. The L2 learners confusion matrix is all over the map. Like every tone can be recognized as any other tone, but with the most confusion centered around these blocks. Well, not to be despaired, right? So diagonal still has the highest number. They're really not doing too badly. But the tone 2, tone 3 are the most confused pairs, but with some other also coming in where native speakers will really make those errors. Okay, so this is the sorting of the item discrimination. I sorted by the top layer of the students. So the way to get this graph is to divide the students by their total score into 3 bands. The top one are the good ones, and this is tone 1. That means we don't have too many errors in the tone 1. Everybody was 100% correct. Most of the items were 100% correct by the high group. The middle groups are actually floating on top group, which means that even if we're just using monosyllable tones, the acoustic property of the tones are enough to differentiate student level. The high groups are higher, the low groups are lower. Very rarely do we have a line poking through the other levels. And then, so some items have high discriminative power like this one. The low ones are very low, the middle one is right in the middle, the high ones are 100% correct. Let me re-emphasize it again. Native speaker has 0 capability of doing it because native speaker has this line and responded very, very quickly. They won't be able to tell you this item has more discriminative power. This is the rising tone, the second tone. You have similar patterns. What you can tell is this tone is harder than tone 1 because even the high group are going from 60% all the way to some items where the high group are getting 100%. Again, the items are typically highly discriminative, meaning the low group and high groups are very, very distinct. This is the third tone. There are a lot of items where everybody's are bad. But there are some highly discriminating items. And this is the falling tone. Again, they're reasonably discriminative. The item discriminative power is fairly good. And then you have some items where the low group and the mid groups are overlapping. You have some items where the mid groups and the high groups are overlapping, but we have enough items that have discriminative power. So here are the background. I think I spent like most of my time giving you the backgrounds. Now, the next one is how do we identify the acoustic properties that are correlated with item discrimination and item difficulty level. Oh, before that, let me show you. How much time do I have? Okay, No problem. So this is the plot to show you the how. This is the plot to show you the red means 0% of the people making errors. The purple means 60% of the people are making errors. Because we have many items who we have people getting some items correct, so we don't have 100% error on any of the items. So what you want is look at the purple color. This one is a rising tone, and it causes a lot of problems for people. And this one is also causing a lot of problem for people because this is confused with that one. And this one, the rising slope is too quick, therefore it's probably confused with that tone. Okay, so these are the individual item, as you saw earlier, which was plotted by distance. Now we're plotting the same item with errors. So these are the second speakers. Again, you see, thinking about the acoustic property of that shape and thinking about the acoustic property of this shape, and they are the shape that cause problems. Now, how do we represent this? So now we will just take the tones and we decompose them with quadratic coefficient. What does that mean? We represent the curve because it's monosyllable tone, and you can see that the shapes are either flat or pretty much linear going down or have one curve. It's monosyllable, so you have one curve. That means we can use this equation to represent the curve. And the coefficient A is represented in this plot, and this is the line for 0 because time cannot be 0. Time cannot be negative. So what you're looking at is this half of the curve. If A is small, if A is 0, that means there's no curve, you get a straight line. So if A is 0, that is the black, you get a flat line. That is a perfect, good representation of the high-level tone, right? Now, this coefficient B is shown in here. Now, again, ignoring the part where time is negative, it doesn't exist. So we are representing this kind of shape with coefficient B. If B is positive and bigger, the rising curve is more straight. But if you come down and have a curve up, you see that some of the tones fit this fairly well, right? So rising tone, the differentiation of rising tone and low rising tones are using somewhere along this line. We can carve that two tones. And then coefficient C is a constant, which means if A and B are 0, Y is just C. That means where it's intersecting with the Y-axis, that means how high the tone is when they start. Okay, so far so good? So now we're representing the tones with this way, and I want to give you 3 references that use this kind of method to represent F0 contour for different applications. Chen Xinhong and his colleagues, Chen Xinhong and his student use vector quantizations. Basically, they use polynomial decomposition and they use more than 3 x2. So they x squared, they use x cubed to represent variations of tone production in speech, natural speech, conversational speech, with sets of quantized coefficients. The coefficients refers to the coefficient A, B, C that we saw earlier. Quantized means that you have to bin them. Otherwise, the probability of each one is just very, very low. And then you learn the association of this representation with text and use that to predict appropriate tone variation for a text-to-speech system. So that's application number one. Application number two, representing green monotones with polynomial coefficient and classified lexical tones. But Androsky and Costello's tone stimulis are like our level 6 recording. It's more like a standard pronunciations of the tone. And you can classify the tones using the coefficients. Okay, the next reference is Esther Grab, who's the person who has a lot of rhythmetrics work, and Greg Korchansky and John Coleman use polynomial decompositions to represent a whole sentence, the same kind of sentence across dialects of British Isles. They classify intonation patterns of 7 dialects in England. And then the intonation patterns was represented by the polynomial coefficients, so they can reduce dimensionality to do classification. Basically, you're classifying dots, that the dots represent the coefficients rather than classifying the whole curve. Okay, so here are how this coefficient work with our distributions of the tone coefficients in our data. This is, let me see. These are the distribution of the coefficient. What you want to see is whether tone 1, tone 2, tone 3, and tone 4 are distinct. And then if they are separated, that means you have a good chance of identifying the tones with this coefficient. But as you can see, we can't use a single coefficient to distinguish the tones. You need to use the combinations of them to classify them. So how do these tones link with the item discriminative? So what kind of property will make the L2 learner identify the tones better or worse? So first of all, let's look at the tones separately. If you have tone 1, then you want a very small B coefficient. And if the B coefficient is small, that means the tone level is pretty straight. Then our learner are all producing those tones, identifying those tones with high accuracy. And if a tone 1 has a bigger B coefficients, then the learner has a hard time. So native speakers can identify big B coefficients, like the non-flat high-level tone, if they have a very high intercept. That is, if a tone is very high, like ma, it's rising in shape, but I'm speaking on top of my pitch range. That means I'm allowing myself to slide into the tone. Therefore, it has a rising shape. A native speaker will identify as a high-level tone. That means native speaker will actually building articulatory constraints into their tone identification. Language learner hasn't have the capability to do that. They say, I want to hear a perfectly flat contour for tone 1. So that's what the story tone 1. The tone 2 prefers negative B value around -1 and -4 that will give you a rising curve without a strongly dipping shape that will confuse it with tone 3. This factor again interact with intercept for native speakers. That is, native speaker will adjust the value of B using different range if the pitch is high or low, and have different expectations, so they're more flexible. The native speakers recognize a particular shape. If they're successful, they carve it into the normal classroom teaching level and expecting the value in a small range. So the red one was the curve drawn by the coefficients, and the dots are the actually tone production. So how about tone 4, which is actually easy? If you have a small positive A and a big negative B, that's a tone 4, and most people learn that. I'm actually skipping the summary of statistics. I told you the interpretation, and here's my conclusion slides. So first of all, we think that adaptive program is most efficient in as a training method, because we can incorporate a highly varied stimuli with a gradual or scaffolding way of presenting the stimuli to train students. We use target listener distance to collect highly variable stimuli for the use of adaptive system, and then we use quadratic coefficient to explain students' performance in an item discrimination. So one potential applications with this will be once we learn from students' performance on the property, or we can make prediction based on the coefficients. Therefore, when the next batch of recording comes in, we can actually analyze their combinations of coefficients and predict the difficulty level of the tone and plug it into the adaptive system and see how it performs. So that is one of the applications of this work. Okay, thank you.
Questions?
Okay, this was very interesting. So a couple of questions. First, a preamble to my first question. Is the four-way tone contrast preserved in whispered speech?
It can, yes.
It is. So how is it done, and is it something that are you also thinking of training your students to hear? Because I suppose it's done by different ways, so can you talk a little bit about that?
So the primary acoustic correlate of tone, or Mandarin tone, is F0. Whisper speech has no F0. So Jose's question is very interesting. How can you identify tone with whisper speech? So there are several different several different conditions. One is some whisper speech are not completely whispered. And that is when we try to whisper to people, we use a little bit of fundamental frequency, but it's very hoarse voice. So if that is the case, you can identify the tone. But we also have true whisper speech. In those cases, different speakers use different strategies. You can manipulate high formants. That is, actually you use your vocal track to create a high formant to change in the shape of the expected tones. And then people can actually hear that and identify the tones. The other is, sorry, managed to finish the talk. Some was, you look at the head shape, head movement of people. They are different ways of manipulating the formant frequency.
So is that something that can be taught in the classroom as well? Are you thinking of teaching that as well? So another question, but kind of related. So you have shown that native speakers use at least two features in order to discriminate between tones. One is the curvature, but then the level of the tone is also something that they use. Have you done any experiments where you manipulate those two features to see which one contributes more and when perception changes depending on tone height?
I haven't done it, but I just researched. Sorry. I just received a prelim proposal on that topic. So. Sorry, I stopped coughing.
So are these tones played to individuals in isolation, like they would hear the word ma or they would hear the word san?
They are the same segments.
Yes. So but what I'm wondering is, in context, a language learner might be able to figure out more easily what the tone is than if there is no context. And I wonder if that's probably true for native speakers as well, but maybe they're better at it. So I was just wondering, if context were provided, if the non-native speakers would be better at identifying which tone it is.
This experiment has no context, and then so this experiment has no context, and that was a deliberate design. Because the students are first-year learners, so they don't know the lexical items much, and so we may not be able to. They may not be able to use context to differentiate tones. Native speakers has tremendous capability to reverse tone from context, in the sense that we don't need tones actually. The information load of tones is surprisingly low. So if people get the tones wrong, so long as it's not monosyllable words, the mama sentence is deceptively confusing. Honestly, I only use that sentence in this talk. I never use that in real life. My mother doesn't have a horse. So yeah, in real life, context differentiated tones.
I missed the part. Do you think that if you did this with first-year students and second-year, third-year, and fourth-year, you would see that item discrimination indices starting to close up?
Oh,
hopefully.
Yes. Hopefully. One thing, I myself is in language teaching in a classroom, but we know that we didn't spend time in the classroom to drill students with tone drills, except for like the first week, when students are so bombarded with all kinds of information, and you throw them the tones. And they say, wow, how can this be possible, right? And then for the rest of the 4 years, we don't do any drills in the classroom. So classroom is very busy with lexical items, everything else. So 4 years later, they get out and they say, oh, now I talk fast enough, I don't need tones anymore. Right? Was someone in Friday's presentation to say, if you talk fast, then yeah, that is really true. If you talk fast, you don't need the tones.
Hi, Professor. Hopefully I won't sound this question, but you had said that 8 feet was a distance that students did really well in because they're used to that in their classroom. So,
It's in our experiment, yes.
Yeah. So isn't there something to be said that maybe, and you want to make the test like the conversation like normal conversations that they would have on the streets with people and stuff, with the words that you chose and the tones and stuff? Wouldn't it be something to be said to have classrooms taught at the distance of when you would talk to people on the street? So for example, if they're used to 8 feet for classroom, decrease the footage so that they'll be used to talking to people on the streets at that, because no one talks 8 feet from each other, normally, real life situation. So I don't know. Do you understand my question?
Yeah, I think we can design some activities in a classroom, like this class is shouting at that class. That may increase language learning a bit because you push them into a very unfamiliar modality, and that actually so we can do an experiment like that.
Yeah, so if you train
can
them,
find a collaborating class.
Yeah, if you train them to have conversations that are normally within like this distance, then later on they'll get used to that tone, hearing that tone in that distance.
Yeah, I'm a believer in using as varied as possible the modality and stimuli to train language learning. I think one of the problems in classroom language teaching is the poverty of the variations of the stimuli. So if there's anything we can do to increase the variations, we may learn better.
Samples of your tests that you use, the adaptive program?
The sample of my test?
The adaptive the test.
I didn't include the sound files in this slide, but my data will be distributed in reciprocity. That is prosody website hosted by Columbia and CUNY for collections of databases for prosody research. So I'm going to give the database for them, and that will be publicly available. Yes?
A comment and a question. First of all, this technique of imagining people farther away to get speakers to increase their pitch range, that's also used by choral conductors who are teaching people how to sing, because quite often people complain, oh, I can't sing that high. And all you have to do is put them through that exercise, and most people can sing higher than they think they can. And the way to get them to do that is imagine that they're yelling to somebody at a farther distance away. So that technique is used there as well.
Great.
I've got a question about ranking the difficulty level of the stimuli. Have you tried item response theory? Because that could be a way to pare down the number of items that you have to use in training, and maybe choose ones that perform better than others.
Yes. Yes and no. We tried that, but we are debating with ourselves on whether we can really apply the item response number on its face value, in the sense that we know native speakers can handle all of this. So basically, we're not excluding any of the stimuli, even though the analysis turned out to be. So we have many numbers where in traditional testing, like ETS testing, will exclude the stimuli. We're deliberately not excluding them because we think these are the things that student needs to learn because native speakers know them. The only ways we will exclude a stimuli is when native speaker got confused on them. They are items like that.
I think we have time for one more question, if there's.
Just wondering, are there any similarities between the items that native speakers get confused on and learners?
Sorry, I didn't hear.
Sorry, are there any? I should talk louder, more clearly.
Go ahead. I'm standing far away.
Yeah. Are there any similarities between the items that native speakers get confused on and that learners get confused on? Is it the same kind of features that people get mixed up about, or not? Yeah.
What we notice the most is that native speakers really scale their A and B coefficient with C. That is, there's a native speaker can handle the interaction of A and B coefficient with pitch height. That is, of course, one condition that is particularly manipulated with this set of experiment. Those are some of the hardest stimuli to identify in lack of distant context. That is, we actually just play back the speech without people knowing where the listener is standing. So we actually make the identification artificially hard that way. So, we think that by more training, learner can learn to give more leverage to the interpretations of coefficient A and B. In particular, allowing drastically different C, in particular when C is very high, then you allow changes that actually fit articulatory explanation. So that is one reason we think maybe that is one reason native speakers don't need to get trained on that one, and they do it automatically because the consequences follow articulatory things. So I think that would be interesting to think about the singing. So if just imagination allow people to do that, then people's interpretations of the tone will also follow.
All right, thank you. We will break for coffee now.
Thank you.